Now, when we understood how we can stop the robot once it hits the wall, which is drive forward while the touch sensor is not pressed, and then stop when it is, we can try, and let's run it, make sure that it works. Excellent. So based on this condition, we can try and create a new one that will instruct our robot to turn 90 degrees to the right. That is a bit of a challenge, but together we can do it. Instead of while touch sensor is false, we would need something like while turn angle is less than 90 degrees. Can we construct such a condition? Let's start with what we know. I'll duplicate the entire program. So now we have that while loop with the condition, and at the end of it, we have a stop block. Now we want to turn to the right. So let's tweak that drive block and make it turn to the right. We will set steering. And can anyone help me with the value we need to make the robot turn to the right? Should it be 0? Should it be 50? Maybe minus 50 or 100? Well, since we need to turn to the right, we would need a positive value. Since there is very little wiggle room in the corridor, it is preferred to make the turn a point turn rather than a curved turn. So we will use the value 100 to create that point turn. Now let's examine the condition. It is understandable that the touch sensor is not relevant here, and so does the false. We want to compare a compared value to be 90 degrees, but we don't know against what to compare it. Any ideas what that thing can be? Write it down in the chat box. To help you out, I'm opening the sensor category. We have here all kinds of sensors reading all kinds of data from the robot. Is there something that can help us? Write it down in the chat box. Esteban, you are correct. Cheryl, you are correct as well. So it is time that we meet a new sensor. Meet the gyro sensor. The gyro sensor or gyroscopic sensor is by far my favorite sensor because it is so interdisciplinary STEM. Let's investigate it just a bit before moving forward. Gyroscopic sensor measures rotational speed or turn rate. A car can drive at 60 miles per hour. That is linear speed. It means that in 1 hour, it will cover a linear distance of 60 miles. Rotational speed is how fast something is rotating. Let's explore an example. Feel free to use it in your STEM class as well, as it relates to more than just robotics. It involves math, physics, and geometry as well. Have a look at the clock. It has 3 hands for seconds, minutes, and hours. Each end revolves around the same center, but at different speeds, different rotational speeds. My first question is easy, but pay attention. What is the turn rate of the second hand? How many degrees per second does it turn? Don't rush, the clock is not ticking. How fast in degrees per second does the second hand turn? The best way to approach it is to see how long it takes it to complete a full circle. 360 degrees are a full rotation, and it takes the second hand 60 seconds to come full circle. So the answer is 360 degrees per 60 seconds, or 6 degrees per second. You can now guess what comes next. My next question, as you might have guessed, is what is the turn rate of the minute hand? How many degrees per second does the minute hand turn? We can see that the second hand is much faster, of course, but by how much? Let's see how long does it take the minute hand to complete a full circle. Full circle is still 360 degrees, and it takes the minute hand 1 hour or 60 minutes to complete. So the answer is 360 degrees per 60 minutes. We can apply some math to it and convert it to degrees per second, which brings a result of 1 degree per 10 seconds, or 1/10 of a degree per 1 second. You can try it at home and check the speed of the hour's hand, but for now we will move on. Now we know that if a car drove for 1 hour at 60 miles per hour, it covered a distance of 60 miles. That is basic even without looking at the equations. If my second hand turned for 60 seconds at a speed of 6 degrees per second, I can calculate to find it turned 360 degrees in total. The gyro sensor does just that. It calculates the total degrees the robot has turned based on the turn rate and total time. We do not need to calculate it ourselves, but while this is the gyro's job, we need to remember this is a calculation of the turn angle, and it is based on time. As such, it is prone to errors, especially at high speeds. That is why it is a good common practice to turn at low speeds. Let's give it a try in our mission.